Hey, welcome back for section 2.4, the last section in chapter 2. Now, chapter 2 has been rough for me because I really want to dig deep into everything, but what I'm seeing right here is just kind of an overview, and especially in this section, because in this section we're going to take a look at scatter plots, correlation, and regression, but we're not going to look at it. We're going to do a very high level overview, because we have a chapter coming up later in the semester where we dig deep into this. So in this session, we're just going to take a look at the idea of what one would do if they had paired data. And we're going to talk about the idea, discuss the idea of correlation and the role of a graph called a scatter plot. And then we'll take a look at the idea of what linear regression is, very briefly talk about it. And then in how that involves an equation and how the graph of a straight line that best fits the sample paired data is used in this sense. Okay, so let's start out with some terminology. Correlation is our first piece of terminology when we're talking about scatter plots. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. And what I mean by that is a correlation exists if you can use the values of one variable in some way to predict the values of the other variable. Right? That's correlation in general. Specifically, linear correlation is when there exists between two variables a correlation that can be approximated using a straight line, or if you think back to your algebra, something of the form y equals m times x plus b, where the m here is our slope and the b here is our y-intercept. And so a linear correlation says, yeah, correlation means one variable can predict the other variable. A linear correlation says one variable can predict the other variable because the relationship is linear. And a slope times one variable can predict the other variable. Right? So in this text, at this level of stats, when we look at correlations, we're going to restrict ourselves to linear correlations. Right? All right. Scatter plot, sometimes called a scatter diagram, but not too much here in the States. I think that's more of a European thing to call them scatter diagrams. But here we call them scatter plots. A scatter plot is a plot of paired data, right, where you have a horizontal axis and a vertical axis. The horizontal axis is used for the first variable in your data pair, and the vertical axis is used for the second variable. We tend to talk a lot about x's and y's because when we speak generically about plotting values, we tend to talk about x's and y's. It doesn't have to be x's and y's. We don't have to call them x's and y's. We just tend to use a lot of algebra-based horizontal is x, vertical is y kind of language because that's where people are comfortable. That's where algebra has made us comfortable. Okay? Here's an example. This is a scatter plot of waist and arm circumference, and the correlation exists between them. So on the horizontal, we have the waist circumference for a data set. On the vertical, we have the arm circumference on the data set. And then every point in this graph, so every point in here, like that guy or that guy or that guy, these all represent some person's waist and arm circumferences. So all of those data points, all of those x, comma, y's that are plotted over there, that's going to be the waist. And that's going to be the arm circumference. Remember, circumference is the measurement all the way around. Okay? And so when I'm looking at this, I'm seeing kind of like a general shotgun approach to this. So data's all over the place, but there appears to be a general trend. Whoops. There appears to be a general trend where the data is going up. Or I could say that there appears to be a linear correlation. Now, I know that there's at least one person there who has taken algebra and says that line does not go through all of those points, and a line's supposed to go through all the points. I'm not going to disagree with you. If this was an algebra class, I would be looking for something like this, where every single line every single point perfectly fit my line. This isn't algebra. This is stats. And stats says, yeah, it's not perfect. Is it pretty much linear? Is there a general overall trend that says when the waist circumference gets larger, the arm circumference also gets larger? And that's what correlation says. Correlation is not going to be perfect. Correlation is going to be a general overall trend. As one variable increases, does the other variable also increase? And could we come up with some sort of equation where the waist circumference would be used to correlate, to predict the arm circumference, where I could find some value for m, the slope of this line right here, and I could find some value for b, the y-intercept, or the arm intercept in this case, of this equation, and then you could tell me somebody's waist size. I could put that number in for w, and then this math would give me a pretty good prediction about that arm circumference. And that's the idea behind correlation. Okay? Now, what would it look like if there was no correlation or no linear correlation? Something like this, where we've got data again, we've got paired data, we've got x, y, if you will, data, where the x is the weight of an individual measured in kilograms, the y is their pulse rate in the beats per minute, and if you look at what's going on here, we've got garbage. And I don't mean the data's bad, I mean that there is no correlation here. I can't use weight as a predictor for pulse. There's not a line that goes through this that makes any sense, because there is no general overall trend to this data. It just looks like a mess. Okay? Now, be careful. Don't fall into the trap of thinking that everything has to be either it's a line or it isn't a line. You could have data that looks like a lot of things. You could have data that looks like this. And then if you think about algebra, I could probably put a parabola through that. Or you could have data that looks like this. And if you think back to your algebra, I could find an exponential function that would model that. Or you could have data that looks like this. Think like the tide at the beach, where it goes up and it goes down, and it goes up and it goes down. And I could find some sort of a trigonometric function that deals with angles and stuff that would model that. So there's lots of different types of correlation out there. We're kind of restricting ourselves here to talk about lines. So we do a lot of linear correlation in this course. We don't talk about these things necessarily in this course. They exist. Right? So while I have an example here of linear, and I have an example here of no correlation, that is not to say that that's all there is in the world. Right? This is just an example of something that I don't know what, I can't put a parabola through there. I can't put an exponential through there. I can't put a wiggly sine wave through that. No, nothing I see here shows any sort of correlation whatsoever. And that's okay. Data doesn't have to correlate. Right? Now, when we talk about our linear correlation, we're going to talk about this idea of a linear correlation coefficient R. And that correlation coefficient, which we call R, the linear correlation coefficient, measures the strength of the linear association. Okay? Now, what do we mean by that? Say the strength of the linear association between the two variables. Well, a strong linear association means that we're looking at something where the data, while not perfect, is pretty darn linear. So if I had data like that, a line goes through there really, really well and is really, really close to all of the points. So this would have a strong linear correlation. Now contrast that to something like this, where we've got more kind of spread out data. It's still generally linear, but the line isn't as good of a fit. So it wouldn't be as strong. And it can get worse. What if you had something that was like that? Well, I mean, there's still kind of a line to it, but it's even worse. So we might say this is weak linear, that's an R, correlation. Okay? We don't have a word for the ones in the middle. We have the words for the good ones, strong. We have good words for weak. We don't have ones for the one in the middle. Right? Now, when we actually calculate R is going to be a computed value. I wanted the highlighter. R is going to be a computed value, and that number is going to be something between -1 and +1 inclusive. Okay? The closer it is to -1 or the closer it is to +1, the better it is. Okay? This first one over here in green, this would have an R close to 1. So if I told you that this had an R of 0.93, yeah, that makes sense. Or maybe 0.90, that would be good. Right? The one over here in red on the right, this one isn't quite as good. So this might have an R of maybe a 0.75, a little bit further away from 1, but still not bad. As it gets weaker, that R is going to get smaller. Like maybe this might only be a 0.43 or something like that. Right? Now you might have noticed that every single example I just gave you was a positive R value. And the reason all those are positive is because all of those lines are increasing. If you had a negative sloped line, you could still have strong linear correlation, but you would have an R value that would be like a -0.88. And that negative would tell me that it's going down rather than going up. The 0.8, because it's close to -1, means I'm strong. Okay? Now we are going to spend an entire chapter later in this book looking at this idea. But just keep this in the back of your mind as we're looking at things. These phrases and these terms are going to show back up, this idea of correlation between variables, between data variables, and then determining whether that correlation is strong or weak. Should we expect to be able to make a prediction with that data? Should we expect to not make a prediction with that data? And then how do I determine whether I should or shouldn't? Right? Section 2.4 is probably the shortest section in here. And we're done